Hello, I'm Jared Skeens, and welcome to the Zoom room. Today, we want to cover part 5 of our trigonometric series. And in part 5, we want to look at identities. So, an identity can be demonstrated by these 3 little lines here. It looks like an equation, looks like an equal sign, but with a third line in it. And it's very subtle. There is a technical difference. I have to admit, I usually just use the equal sign. But what that means is that one side is congruent to the other side, or one side is identical with the other side, such as identity. Or you could say, probably more accurately, one side is the same as the other side. So because it's the same, you can replace the one expression with the other. And that's what we're going to be using in our trigonometry, is these identities that we replace an expression with an equivalent value. So basically what makes it different from an equation is an identity is true for all values. So these identities that you see up here have a theta in them. For all values of theta, these identities are true. Whereas with an equation, what you're looking for are the specific values that theta can take in order to make it a true statement. So not all values make it a true statement. Only certain values make it a true statement, and you're solving for those particular values. So what we're going to see in Cambridge is they actually like to pair up in their question type identities with solving. And this is the main question type. Now, we've had 4 other parts to the series that have built the foundations and have gotten into some of the other details, but the bulk of Cambridge questions is focused on identities and solving. So the first part will be an identity that you prove or show to be true, and then that you've established an identity, you're going to use that in the solving process to find the particular values of an equation. So today in part 5, we're only going to focus on the identities. Then the next time in part 6, we will focus on the solving. Okay, but before we get to the questions involving identities, I want to first explain the identities that we're going to be working with and how we can understand them, so that when we get to the questions, we're a little bit more comfortable with those substitutions that we're making. So first thing that I'm going to start with is over here on the left, we have sine of a negative theta compared to sine of theta. Now, we discussed this actually in the, I think it was the part 1 in one of the foundational parts of the series, how that when we're dealing with our unit circle, we're standing at the origin and we're facing the 0 degree. That's our orientation, facing the 0 degree, the positive x-axis. And when we rotate counterclockwise, that is the positive theta direction. Rotating counterclockwise is the positive theta direction. And if we rotate clockwise, that's rotating in the negative direction. So just like with your xy axis, you have a positive x and a negative x, positive y and a negative y. Negatives oftentimes are used to indicate change in direction or opposite direction. So positive theta rotates counterclockwise, negative theta rotates clockwise. So how does that affect our trig functions? Well, remember that sine is the opposite value. Sine is the opposite value. And when we rotate in the positive direction, the opposite value is going up. So you remember sine from Sekolah, sine is opposite over hypotenuse. The opposite value is going up. But if we rotate in the negative direction, the opposite side is going down. The length of the side is actually the same for the same angle. So for a particular value of theta, that opposite side will be the same length, but the lengths are going in two different directions. One is going up, the other one is going down. So what we can say then is sine of a negative theta is the same thing of sine of theta, but in the opposite direction. So this becomes an identity. Sine of negative theta is same as sine of theta, but in the opposite direction. Sine of theta, but in the opposite direction. So what this identity allows us to do, maybe when we're working with trigonometry and we see a negative angle, we're like, what do I do with that negative? Well, this identity allows us to take it out and just move it to the front so that we don't have to worry about it, or we can treat it like a normal negative sign. Then we have cosine. How does it affect cosine? Well, here you can see that cosine is, remember from Sekolah, cosine is adjacent over hypotenuse. So cosine is the adjacent side of the triangle. And if you notice, if we go up, this is the adjacent side. If we go in the negative direction, it's still the adjacent side. So the adjacent side is the same whether you're rotating in the positive theta direction or in the negative theta direction. The adjacent side stays the same. So when we see a cosine of negative theta, we can just discard the negative because it is identical to or the same as cosine of theta. Okay, so that makes it easier. Now, what do you think about tangent negative theta? I'll let you think about that, and we're going to look at what is tangent theta. Now, we did already mention this in previous parts because you should have learned it in previous math classes prior to this. Remember, we're focusing on Cambridge for Pure Maths 1. So this should be review, but it is also a key identity that we're going to be working with in the Cambridge Pure Math 1. So just to review it one more time, tangent in Sekolah, tangent is opposite over adjacent. So when we look at this unit circle, from the angle, our point of orientation here, the opposite is the sine function. The adjacent is the cosine function. So tangent is actually a combination of sine and cosine. So like I've said before, the entire trigonometric system is built on sine and cosine. Those are the Lego blocks that build the entire trigonometric system. So even though tangent is what we consider part of the three basic trig functions, it is actually composed of sine and cosine itself. So now that we've looked at that, let's go back to this question. What do you think tan of negative theta would be? Well, remember all students take calculus? All are positive here. Sine is positive, tangent is positive, cosine is positive. So with sine was positive up here, but negative down here, and that's why the sign changed, because it was positive and then negative. But with cosine Cosine is positive in both quadrants. And that's why it didn't matter which way you rotated the angle, because it's positive in both. So you get the same value. So what about tangent? Well, if you're dividing sine by cosine, and you divide a positive by a positive in the first quadrant, positive sine by positive, you still get positive. Tangent will be positive. All are positive in first quadrant. In the fourth quadrant, the opposite is negative. Negative divided by positive is negative. So a tangent in the fourth quadrant will be negative. Only cosine is positive. So tangent of a negative theta will act just like sine. Tangent of a negative theta will be the same as a negative tangent of theta. So tangent follows the same thing as the sine function does with respect to positive and negative angles. Now, back to the tangent. Remember in a past video I mentioned that you learn algebra first. Algebra is the natural step past the basic math where you get into the unknown variable and you start to develop your algebraic platform. Once you get so far into the algebra, then you can start with your trigonometry. And the reason why we do algebra first is because your trigonometry actually uses a lot of your algebraic principles. And so we follow along. Once you've learned some algebra, you then are able to apply that to the trigonometry. Of course, the trigonometry ends with the trigonometric twist, but how to get there generally follows algebraic principles. So if we look for those algebraic connections, it can help you bridge those two systems and see how they're just different ways of looking at the same thing. That's what math is. Math is about modeling reality. And sometimes there's more than one way to model the same reality. Just like we saw, a point on the graph can be represented with X and then Y. It can also be represented with an angle rotation and then a certain distance in that particular direction. So both of them are ways of modeling the same location in reality. So let's look at our algebraic connection here. Something to just keep in the back of your mind. It's not commonly found in questions, but it's an important connection that you should be able to have in your thinking. And that is tangent is sine over cosine. And one of the things that we learned in algebra that relates to y over x is slope. Slope is the change in y over the change in x. So if we want to find the slope of the line, if we want to find the slope of the line, we find the rise over the run, the change in y over the change in x, or the sine over the cosine. In other words, slope in algebra functions the same way as tangent does in trigonometry. Tangent can be used to find slope. Another thing that we could do in algebra, if we wanted to, if we know the slope, if we have our line and we know the slope of the line, we could find the angle that that line makes with the x-axis, or really with any horizontal line that we want to take. So whether it's the x-axis or something higher, the line will still come through at the same angle. So if we want to find that angle, this is something that can enrich the algebra a little bit. If we know the slope, we can take the inverse tangent of the slope and find the angle of our line. So it just gives us an extra piece of information. Now, back to our identities. We want to go to one more identity, and this one is also an algebraic connection. Remember in algebra, when you have a right triangle, you can use the Pythagorean theorem. A squared plus B squared equals C squared. So if we apply that to our trigonometry, we get sine squared plus cosine squared equals 1 squared. And 1 squared, of course, is just 1. So we have another identity. In fact, this identity is called the Pythagorean identity. Even though it's using trig functions, these trig functions are the sides of a right triangle. And so this is your Pythagorean theorem applied to trigonometry. And you should also be able, because algebra is important, you should be able to manipulate this identity. In other words, don't get it rigid as it only can be one way. You can algebraically manipulate it. So if you subtract the cosine squared to the other side, you get sine squared theta equals 1 minus cosine squared theta. Or if you subtract the sine squared to the other side, you get cosine squared theta equals 1 minus sine squared theta. So you have actually, and I'll make them identities here instead of equations. So each left side is the same as the right side, meaning you can replace one with the other. And obviously with sine squared plus cosine squared, that looks complicated. You replace it with a 1, much more simple. Sometimes you don't want a sine. Maybe you want everything in cosine, or maybe you want everything in sine. And so these identities allow you to make substitutions, replacements that can help you smooth out the math. But between those is basically all algebra, okay? So what we're gonna do now is I'm gonna set up some questions for you so that you can see how this works on Cambridge questions, okay? Okay, here we are with our first question. And what we have is the first part of the question says, prove that this side is the same as this side over here. Now notice I put a little gap here. On these questions, it's either going to say prove or show, and you need to demonstrate the left becomes the right. Now, it kind of depends on curriculum and teachers as to how much they allow you to use the right-hand side. Actually, the goal is not to manipulate the right-hand side. You want to take the left and only work with the left. So you're not working with it as an equation. You're working with it as an expression, and you're going to change this expression into that expression. And that's going to be important for Cambridge. Now, sometimes other curriculum and maybe teachers will let you cheat a little bit and let you work both sides to the middle, as long as in the middle you have equivalent expressions. And there's really nothing wrong with that. But for Cambridge questions, you really don't want to mess with the right-hand side. And the reason is after you demonstrate this, you're then going to move into the second part of the question, which we'll cover in part 6, the solving part. And they're going to have kind of a nasty looking equation set up for you. But because you already did this proof, you can substitute out the kind of nasty looking part, the more complicated looking part, and put into its place the simplified part. And then so you can move forward with your problem solving without having to go through all this work. So it splits it up for you into 2 stages. Stage 1, the identity part. Stage 2, the solving part, okay? So for Cambridge, we don't want to work with the right-hand side. That's why I moved it over. We're gonna work with this. Now, there's 2 kinds of students, and we're gonna find out which kind of student you are. One kind of student looks at math and just says, just tell me what to do. I just want to do it. I just want to get the answer. I just want to submit my homework and just be done. Then there's the kind of student who says, I want to understand what I'm doing. And that's really the goal of math. Math is not about doing. It's understanding what you're doing. And this type of problem, or this problem type, really will show you what kind of a student you are. Because you can't just memorize a procedure. There is not one procedure that you can follow with identities. Really, all of your algebraic skill set is a prerequisite for working your way through and making step-by-step decisions to get to the end product. And it doesn't always follow the same pathway. So you have to think about what you're doing. And the only way that you can really think about what you're doing is if you understand the choices that are in front of you. So you got to be able to recognize those algebraic situations and make choices based on that. So if you're a student who likes to memorize, maybe you can even memorize how to derive the quadratic formula. Many steps, but you just memorize it and say, yeah, I can do it. This isn't like that. Okay, you can't just memorize it. You gotta think your way through it. So I really like this question type because it forces us to understand the options and weigh the options and make evaluations and judgments as we move along. Now, there's a second reason why I like this type of question. I like it because you already have the answer. Usually in a solving situation, they just say solve. They don't give you the answer, so you got to figure it out. And when you get to the end, unless you plug it back in to verify that what you have is actually right, you get to the end, you don't really know. You have to take extra time to double check. With this one, when we get to the end, we know we got it. Okay, so I really like these. I like it because it makes us think about what we're doing. You can't memorize just a pattern. And I also like it because we already can see the answer, so we know where we're going. Here's our destination. And really, that's something you really need to remember. You can algebraically do a lot of things to this. Okay? You can follow algebraic rules, and you can actually go off in any of a number of directions and still technically be correct. But we want to make sure that we end up with this outcome. Okay, so always look at the end to help guide you in your choice process, because the form of this is what's important. Okay, so keep that in mind. So when I look at this and I look at that, I see nothing in common. This has all cosine. There's no cosine over there, although there is one hidden inside the tangent. There's no sine over here. There is over there. All ones, there's a 4. No, you cannot go 1 plus 1 plus 1 plus 1 is 4. It doesn't work like that. So be careful to follow your algebraic rules. That's where a lot of students get off track, is when they try to take shortcuts or they start canceling, like here's a cosine on top and here's a cosine on bottom, and they just cancel it out. They go like, see, this is divide. Cosine divide by cosine. You can't do that. This division is going across add and subtract. Division does not cancel add or subtract. It cancels multiplication. So don't get hasty to just cancel and make up your own math rules. It follows everything you learn from algebra. Okay? So what do you do when you have an expression? Remember, we're not treating it as an equation. When you have an expression with fractions in algebra, what do? Well, hopefully what comes to your mind is you get a common denominator. So that is going to be our first step here. So our denominator of this one, here's our division bar. So this is 1 unit, not 2 separate parts. That's 1 unit, 1 denominator, and here is our other denominator. So here's 1 minus cosine theta. We need a 1 plus cosine theta. And whatever you do to the bottom part of a fraction, you have to do to the top part in order to maintain the equality of the fraction. right? Because anything divided by itself cancels out. Well, we want to put it back in. So 1 plus cosine theta. Notice this is a value of 1. It's not changing the value of this fraction here. What we do to the denominator, we do to the numerator. Over here on this one, we have the 1 plus. We need the 1 minus. So 1 minus cosine theta. And I need to put this in parentheses so that it's distributing and not just multiplying by the cosine. So be careful with your use of parentheses. Notice this one needs parentheses. It's not just multiplying the 1, it's multiplying by this whole top thing. So I noticed that sometimes students are not careful with their parentheses and they end up making incorrect distribution because they incorrectly use parentheses or they don't use when they should have used, okay? So be careful with your math. Here we multiply. Remember, use the smiley face method. This one times this times this, the nose and the mouth. You get a little smiley face. And what we end up with is 1 plus 2 cosine theta plus cosine squared theta minus, but notice the minus sign is between the fractions. Very important. It is not this minus sign that is within the fraction. When the negative sign is in front of the whole fraction, it means it distributes to the whole fraction, okay? So this is one of those times you need a parenthesis. Many times students forget to put it, and that negative sign only ends up on the first term, and they don't distribute it to the whole thing. And so we're only 2 steps into our process, and if you get this wrong just because of distributing a negative through your fraction, we're in trouble. So careful with your algebra. 1 times 1 is 1. A negative cosine and a negative cosine is a negative 2 cosine. And then a negative times negative is a positive cosine squared theta. All over. Now we can make 1 denominator because as you see, our denominator is now a common denominator. So all we have to do is multiply one of these. You should also recognize this as a difference of squares, meaning the nose and the mouth will cancel out. A positive 1 cosine and a negative 1 cosine gone. All you get is the 1 and the negative cosine squared theta. So just like in algebra, you have difference of squares. Guess what? Trigonometry has difference of squares. Everything you learned about factoring, fractions, multiplying, dividing, all of that in algebra applies to trigonometry, okay? So now that we got this, we want to simplify the top. Now I'm just going to use equal signs because we're just working with this expression over here. We'll just leave our identity statement over here on the right. That's our goal to get to. So 1 minus 1, gone. 2 minus a negative, remember this distributes. So this negative is distributing to all 3 of these parts. So a negative minus a negative means plus. So we end up with 4 cosine theta, and a cosine squared minus cosine squared also cancels out. So now we have this over 1 minus cosine squared theta. Remember, in trigonometry, trig functions always have an angle. You never see a trig function without the argument being the theta or sometimes an x. So don't just write cosine, sine, make sure you put the argument, the theta. Sometimes you can, if you want to shorten it, you can just use CST like that, without writing the whole thing. But don't get into a bad habit of not writing the argument with the trig function. There is no such thing as just a cosine. It's cosine of an angle, okay? So don't have time to really explain that more, but don't forget your argument. Some people do, and then they don't know what they're working with. Now we want to look for or look at this, and again, keep in mind of where we're going. So we see the 4 now, that's developed, that's good, but everything else doesn't quite look right or doesn't match. So what we want to do now, because we've combined our fractions, let's look at our identities. And if you remember, we can manipulate our Pythagorean identity here. Here is a 1 minus cosine squared. If we just subtract the cosine squared to the other side, like we did a little bit ago, sine squared is same as 1 minus cosine squared, right? If we subtract cosine squared, we can get 1 minus cosine squared theta. So this then becomes our identity where we're going to trade out, we're going to substitute out this right here for our identity and change it into a sine squared. Why? Well, we see a sine over here, so we need a sine to get in somehow. So this becomes 4 cosine theta over sine squared theta. Well, there's only one sine theta, and don't know what happens to the cosine yet. So let's split this apart into its components. 4 times cosine theta over, and let's separate the sine theta to be sine theta times sine theta. So sine squared is just sine times sine, right? So notice that we now see the sine and we see the 4. We want to keep those because they're right here. Somehow we got to get a tangent. Now, tangent is sine over cosine. Well, we have the sine, we need the cosine. So we're going to introduce that in. We're going to divide the bottom by cosine so that we can get that tangent. But whatever we do to the denominator, we have to do to the numerator. Up here, we multiplied top and bottom by the same thing. Down here, we're going to divide top and bottom by the same thing. Okay? So if we divide the top by cosine theta, now all of it, and this is multiplication, division and multiplication are allowed to cancel. So that cancels out. This we don't want to cancel, it doesn't. We want it to now use the identity and turn into a tangent. So we get 4 over sine theta tan theta. And there we have arrived at the destination that this particular question wants us to arrive at. Now, in part 6, with solving, we're going to come back to this. We're going to come back to the same example, and then we're going to move forward where this identity that we've just proven, we now can use into an equation and then move forward to solve the equation. But I want to separate the identity algebraic work from the solving process, although they're similar, but kind of two different outcomes that we're looking for. Okay, so this is the first example. I'll set up a second one and we'll look at some of the similarities and differences. Okay, here's our second question. And notice in our second question, it starts with the word show. Show and prove, basically the same thing. And notice again, I put space in the identity. We want to demonstrate or show that cosine to the 4th power x is the same as 1 minus sine squared x plus sine to the 4th x. Now at first, you might be like, wow, what? I don't even know where to start, what to do. There's no fractions. This is just one term. That's three terms. This is just a cosine. This is a constant, sine squared, sine to the fourth. How do we get there? Well, when there's no obvious algebraic steps to take, obviously look at your end outcome that you want to get to. That doesn't really help us right now, but also look at your identities. By the way, these identities are in your formula sheet that Cambridge provides for you. So you don't necessarily have to memorize them, although you'll probably be working with them enough where you'll memorize them anyway. So here is a cosine to the fourth. Well, I don't see any cosine to the fourth up here, but the cosines that I see are either cosine or cosine squared. Well, cosine squared can make up cosine to the fourth. We just need to break this up into cosine squared x times cosine squared x. So we just break it apart. Actually, it's like factoring, kind of factoring it into that. You could also have written it as a square. You could have written it as cosine squared x squared. That would be the same thing, but I prefer to write it like a multiply. And now we can look at cosine squared. Well, remember our cosine squared, we could also make an identity by subtracting the sine squared over. Right? So our identities right now are written in theta. Our current problem is written in x. So try to make sure you stay in the same variable your problem is using. And again, for me, I try to be consistent if I'm working with degrees. I work with theta. If I'm working with radians, I use x. But really with identities, it doesn't matter because you're not solving for degrees or radians at this point. That's in the next part. So we can replace the cosine squared with the 1 minus sine squared. So this becomes a 1 minus sine squared x, 1 minus sine squared x. Now we do our smiley face method. We got our binomial expansion here. This one times this one. Here's our little smiley face. And what we end up with is 1 times 1 is 1. A negative sine squared and a negative sine squared is a negative 2 sine squared x. And then a negative sine squared x times a negative sine squared x, and then positive sine to the fourth x. Remember, when you're multiplying, you add exponents. Just like in algebra, multiply, add exponents, multiply like bases, you add exponents. Same thing here, our like base is now a trigonometric instead of algebraic, and we still add exponents, we get fourth. And what do you know? That's exactly what we need. So it actually went really fast, but your options at the beginning were a little bit not sure maybe what to do because you don't see the things like the fractions, and there's even no operations there except for the exponent. So some of this can actually go more quickly than what you might think when you make the observations, the correct observations that you need to, okay? So I'll set this up again and we'll look at, okay, here we go with problem number 3. Again, we see our instructions to prove, so we know this is an identities type question. We see the left side, I've separated it from the right. This is our goal, this is what we want to arrive at, and this is what we have to work with. So similar to our first question, we see fractions being added or subtracted. In algebra, you get common denominator. So we jump right into that. We see that we need a sine theta over there. Over here, we need the 1 plus cosine theta. So this is our common denominator. Whatever we do to the denominator, we need to also do to the numerator. Then we can multiply this out. Again, be careful in your multiplication. So we end up with 1 times 1 plus cosine and cosine 2 cosine theta, and then plus cosine squared theta, plus, and we don't really need the parentheses because distributing a positive doesn't affect the rest of it like distributing a negative that we had the last time. So we don't really need the parentheses. Sine times sine is just sine squared theta anyway, over. Now on the bottom, we're not going to multiply it out. You say, how do you know when to multiply it out or when not to? Well, again, look at the end result. At the end result, we see a sign. So we already see a sign there. We don't want to make it more complex by blending it in the multiplication process. We want it to stay separate because we want to see it show up in our end result. And usually in algebra, you don't multiply out the bottom anyway. It's the top that needs to simplify because it's joined by add or subtract. In the denominator, it's already joined by multiplication, and this is division. So we want to keep it in the factored form unless we see that we need to change it. Keep it in the factored form. That way, if something can cancel, it's already, ready to go, because division and multiplication are opposites. So we don't want to turn it back into the polynomial form unless there's a reason to. So we're going to keep this separate. So sine theta times 1 plus cosine theta. So we can already see that this sine theta is there where we want it. Okay? And we're going to leave this in its factored form. This is multiply, which is the opposite of divide. So we're okay on the bottom for now. We want to simplify the top. Now, when we look to simplify the top, at first, we don't see any like terms. There's a 1 constant, no other constants. There's a cosine to the first power that is not the same as cosine squared. Just like in algebra, x and x squared are two different terms. They're not like terms. Cannot combine those. And then we have a sine squared. So the top, at first glance, does not simplify as far as adding like terms. So then we look to our identities and we go, oh yes, sine squared plus cosine squared equals 1. So right here we have an identity. This can be replaced with a 1. So now we have 1 plus 1 is now 2 plus, we still have this 2 cosine theta over sine theta and 1 plus cosine theta. Now again, do not get too hasty. Don't jump ahead of yourself. Don't go, oh, this is multiply, here's a cosine, there's a cosine, and just start canceling things out. It doesn't work like that. Follow the proper algebraic steps. So what do we need now? Well, we need the 2, but we need the 2 by itself. Well, notice there's a 2 common to both the terms in the numerator. So we can factor out the 2. And when we factor out the 2, we're left with 1 plus cosine theta. And now all of a sudden it becomes obvious, or it should be obvious, what we can do now. Now we have a multiplication both in the top and in the bottom with a division in between. Division and multiplication are opposites. This 1 plus theta occurs both top and bottom. Now we can cancel it out and we arrive at 2 over sine theta, which is exactly what we want. Okay, so you're starting to get the feel for how this works? Hope so. We're going to do one more question together and we'll go from there. Okay, we're back with the last problem that we're going to do for this particular part in our series. And here we have, again, it says prove This time we have a parenthesis squared with on the inside 1 over cosine theta minus tan theta. And we have to demonstrate that this is the same as 1 minus sine theta over 1 plus sine theta. So we look at what we want to get to, and of course it doesn't look anything like that. Well, we see that we have a square. So you might think, well, let's multiply it up. Well, before we do that, notice we have no tangent over here. No tangent. And we do have a tangent here. So we might want to consider our identity before we start squaring everything out. Because if we square this out with the tangent in it, we're going to get a bunch of tangents. And if there's no tangents, we don't want more. We want less. So let's consider our identity at the beginning, and notice there's a cosine in the denominator and a cosine in the denominator. That would be really good because it gives us a common denominator. So this can be expressed as, using our identity for tangent, this can be expressed as 1 minus sine theta over cosine theta squared. And I hope I didn't do too many steps at once. Tangent is sine over cosine. So 1 minus sine is on top. Cosine is the denominator here. Cosine is the denominator there, meaning we already have a common denominator. So the division bar can go all the way across, and we just write the denominator once. We don't need to write two separate denominators because it's already common denominator. And we still have the square on the outside. So now we've eliminated the tangent, and now we see the sine show up, and that's good news because we see sine over here. Now, when we go to square this, do we expand the numerator? Now, in the previous problem I just mentioned, we usually expand the numerator so that we can simplify it. But again, keep in mind where you want to go. In our outcome, we want a 1 minus sign on the top. And we already have a 1 minus sign. So if we expand it, if we multiply it out, we're going to lose that. We don't want to lose it. So while normally we would expand and simplify the top, in this case, we're going to hold back and wait and see what happens. So we get, I will separate it because notice there's only one, not two factors. So I'll separate it, 1 minus sine theta times 1 minus sine theta. So instead of expanding it out, I just write it like a multiply over cosine squared is now cosine squared theta, okay? Well, we've got one of the factors on top that we want. Notice there's no cosine squared on the bottom. So we go back to our identities and we look and go, yes, we have a cosine squared. We can replace it with 1 minus sine squared. So 1 minus sine theta. You got to be a little patient because sometimes you finding yourself rewriting a lot of stuff over again. You got to be patient and do your line by line work. Now, when we get to this, we've replaced, notice we've replaced our tangent. That was one identity. And we've also replaced our cosine squared. So we've used the identities. Now we got to figure out how to get this to look like that. Now here's another algebraic thing I actually hinted to in one of the previous questions, and that is in algebra, you have difference of squares. Don't forget difference of squares. Both of these identities are actually difference of squares, okay? So let's treat this like a difference of squares and see what happens. So we get 1 minus sine theta, 1 minus sine theta over, and if this is a difference of squares, this is a 1 plus sine theta times 1 minus sine theta. So it really helps if you're good at factoring, because you're going to do a lot of algebraic factoring with trigonometric expressions or equations as you move forward. So don't lose your skill set from algebra. It's extremely important in the trigonometric platform. So here we recognize the difference of squares. We now have product on the bottom, product on top, separated by division. Now we can cancel these out. And what do you know? What we end up with, 1 minus sine theta all over 1 plus sine theta. And that is exactly what we want. So that brings us to the end of part 5. We went over 4 different types of problems, all from Cambridge past papers, to help you get the idea of what you're doing with these identities. And like you can see, there's no one pattern of procedure that you're following. You're making step-by-step evaluation decision using your algebra as prerequisite to work your way through to get from the left side and make it become what you see on the right side. Okay, so next time in part 6, we'll do the solving. We'll see how this translates into the other part where we get into solving. And so I'll see you again next time. Thank you for joining me in the Zoom room.